Welcome back. It's been another 6 weeks, and this week we have Rust 1.74. As always, Rust 1.74 is available via RustUp, and if you don't want to just update stable, you can run RustUp update without stable and get everything. And as always, we have a set of examples to talk about today. The very first one I want to talk about is lint configuration. And one place specifically that linting is really often an issue, but is a false issue, is in Bevy apps. So in Bevy apps, you have this app that you set up with systems, and these systems are provided resources via dependency injection. So you can end up triggering 2 Clippy lints, even though there's nothing you can really do about it. First, we see this query for the AABB gizmos here with a transform, change sprite without global transform. This is a nonsense query. Don't pay attention too much to it, but this is similar to some code that you would write if you were building a Bevy app. And this code triggers the type complexity Clippy lint. The second issue is that Bevy systems often can have a lot of different arguments to these functions. So if you hit more than 7, you'll trigger the Clippy lint for this function has too many arguments. Semi-related, but we'll cover it in a second, is I've put some unsafe code inside of this system. It doesn't really do anything per se, it just exists to be some unsafe code. So how it used to work is we used to be able to, at the top of the file, to allow a Clippy lint, for example. And that gets rid of these lints that really don't apply to Bevy projects. We can also do this for Rust C. So if I forbid unsafe code, Clippy will let me know that I have an unsafe block here. And this actually happens to cargo build as well. So we've got Rust C lints, which are something you always want to follow effectively. And we've got Clippy lints, which could be wrong in certain circumstances for a given project, such as Bevy. So if I comment these back out, we can see that we still get these warnings. And now in Rust 1.74, we can put these lints inside of the cargo toml instead of needing to scatter them in the files. So now when we run cargo Clippy, we don't see those warnings. When we run cargo build, we do get this usage of an unsafe block that we don't want. So we have forbidden the unsafe code lint in Rust C, and we've allowed the type complexity and too many arguments lints, which means that we don't have to follow them anymore. They aren't going to warn us a million times in our Bevy apps. Now this is really great, but we can do even better. And let's say I have a bunch of projects. This is a workspace. It's got a bunch of examples that are different projects and a cargo toml at the root. So if we do lints workspace equals true, and we go up to the workspace, we can leave workspace lints Rust and workspace lints Clippy and get the same effect. So really happy about this. This is going into all of my Bevy projects for sure, because those Clippy lints don't really make sense for Bevy projects. Moving from Bevy and linting into cargo, there are 2 cargo related features in this release: credential providers and authenticated private registries. Now there definitely is this list of third-party registries, whether they are commercial in this part of the list or open source that you can run yourself. And these features make it easier to have a secure connection to those registries. I unfortunately didn't stand up a whole registry for this video, so we're just going to move on. But if you're using a third-party registry, this will be really good for you down the road. Next, we've got a feature that is kind of a stepping stone on the way to 1.75, which we'll talk about when 1.75 lands. But this is the stabilization of impl trait projections. A lot of fancy words. What this basically means is that we've got this struct here, and we want to return something like impl iterator. This is return position impl trait, or RPIT. And if we try to run all this code with 1.73, we get impl trait return type cannot contain a projection or self that references lifetimes from a parent scope. So we've got self here. Self is returning items of wrapper. Wrapper contains a lifetime to some data. Wrapper is a nonsense type that kind of just takes any lifetime and takes any type and stores a shared reference to that type. So self then refers to the lifetime of whatever data we're storing in that wrapper. And if you haven't run into this, it's not really going to matter that much to you because it works as expected now, whereas before there was kind of a hard-coded, this had to be static lifetime kind of thing. So this is the code. We've got a struct that has some references. We've got an impl for that wrapper. That function down here is used as wrapper with some lifetime, some type. Everything is implemented on unit here. So it's a little bit abstract, but you can take this as one type, and then we're calling an associated function called impl trait, which is just what this function is called. It's not a special name at all. And then we're collecting this impl iterator with those references to self into this vec. So the key here is that self can now have these references that are non-static. The same is true for traits. So this trait has a lifetime of A and some associated type. We mark that associated type, or we implement this for unit. We say the associated type is unit. We have a new function that returns unit. And then this implementation is also kind of nonsense because we've got this lifetime A that the trait is using and the wrapper is using. Our type T has to implement the trait. So we're implementing with these generics some wrapper that uses the generic lifetime and the generic type and defines this function a few assocs or associations, I guess this could be. And then we've got this return position impl trait again that uses that associated type in the return value. And this associated type again has references through to all these lifetimes. And now you can do this. So in this case, we don't actually have access to anything. So the only thing we can do is really construct an empty vec that we turn into an iterator and return, which you can see down here. And if we run this, you can see these values if that helps. Again, this is pretty abstract. I had to do a little bit of work to make it actually work. This is the example that was described in the blog post, but I've filled in all of this extra code so that this code does actually run if you do want to try to check this out. Those are the major features, so let's get into the stabilizations. The first one is kind of cool. It's this saturating type. So we've got two options for using this. We can wrap some numeric type in saturating, in which case we have to construct it with the saturating, constructor here. So we've got this 10 wrapped in saturating. We're going to call this a clamped CSS color. What saturating means is that since we're using a U8 here, we have values from 0 to 255. And the saturating part of this means that we can't go above 255 and we can't go below 0. So normally what would happen here is that these numbers would overflow or underflow. In debug mode, when you're compiling in the dev profile, you would be warned that something was overflowing or underflowing. But in production, that warning gets taken away. But sometimes what you want is actually saturating semantics. So this kind of clamping from 0 to 255. And we can see that clamping in effect here. We're doing 3 loops. We start off with a clamped CSS color, which, 0 to 255, maybe this is the color red in our CSS color. We take that CSS color, we multiply it by 2. In this case, we're using the saturating type here to construct our U8. So we have to use the saturating type again when we're multiplying by it, and then we debug that out. And you can see over here that the first iteration we get 20, then 40, then 60, or 160, and then it hits 255 because the number would have been 320, and it stays at 255 that entire time. So it's clamped at that top value. And then if we subtract, which we're doing the same thing here, we're subtracting 50 for each loop. That goes down to 205, 155, 105, 55, 5, and then clamps at 0. So you can't overflow or underflow. You can only clamp to that top or low value. The other way to use this is to just have a U8 that you already have and then use the saturating functions for operating on it. So we've got a regular U8 that's just the number 10. This should overflow or underflow. But in our case, since we're using the saturating multiplication function, we can pass in the number 2, and this will go 20, 40, 80, 160, and then clamp at 255 like we saw before. So you can do this on just any old number, or you can do this on types that you want to make sure are using saturating semantics. So this is very cool. Moving on from saturating numbers, we're going to talk a little bit about standard in and standard out, or more accurately, standard out and standard error. So here we have a couple of commands. This first command that I'm building is who am I, and the second one is ls. This is a way of basically building commands that you can then run from Rust. So in this case, I'm running who am I, which is a CLI command. If I run who am I over here, this is the same thing. It should just say Chris because that's my username. So in this case, we're taking the standard out of that command and we're redirecting it to IO standard out, which is our processes standard out. It's the program that we're running. Then we debug the output status and assert that standard out from the command is empty because we've redirected it. We've redirected it to this standard out. It shouldn't exist in our command standard out anymore. So if we run this, we can see that the who am I gets redirected to our cargo process here, just my standard out in my terminal. We get the output of who am I here. Then we get our debugs. So the output status is this on line 9. It's an exit code of 0. Wonderful. And then our output standard out is empty. If we didn't have this redirect here, this wouldn't pass. So we're asserting that our standard out on the command is empty. And you also see that the who am I output is missing from our standard out over here. So the specific traits that are being implemented here are from IO standard out for process standard out. And the same thing for standard error. And you can see that if we have ls down here and we give it an argument of some directory that doesn't exist. So this is doing ls, a directory that doesn't exist. And I'm using new shell, so I get to this fancy error message, but you will also get an error message. If we run the application, we'll see ls, a directory doesn't exist, no such file or directory. So we are redirecting that standard error to this standard out. And again, that is the implementation of from IO standard out and IO standard error for process standard out and process. And it doesn't matter what combination you use here, standard error, standard out, yada, yada, yada. You can do whatever piping you want to here. In this release, we also get access to the internals of OSSTR and OSString. These exist, if you're not aware, because there are platforms that have existed in the past that don't have UTF-8 file paths and things like that. So if you get an OS string, it might not be valid UTF-8, but now we can get at the internals of these strings. I would say that if you're looking to do this for some reason, maybe second guess yourself. There is a wonderful UTF-8 path package, for example, if you're dealing with paths and you probably want UTF-8 unless you really know you don't, but it is here if you want to get access to the internals. From IO to more IO, in this case, errors. We now have access to standard IO error, other as an associated function, and this is just a convenience function for creating an IO custom error with a kind of other and some, error here. So in this case, we're using some custom error, and we have to wrap that in ERR to actually return it to, the main, the IO result. And we see that we do get this error constructed for us. From error to cars and U16s, we have the implementation of try from car for U16. So on the right-hand side here, we can see my cars, which I've made a vec. This could have been a string and we could have called cars instead of into iter, but I thought it would be clearer if I used a vec here. So we've got cars. So this is the car 0, the car C, and then a couple of them that I actually don't know the names of off the top of my head, but we can take those cars and iterate over them. So C is a car. If we look at the types here, you can see that. And we get U16 try from C, which gives us a result that we unwrap, and then we get a U16. That U16 is 48 for 0, 99 for C, 255 for this one, and then 994 for the next one. So it's the UTF-8 index of these characters. There are ways that you can cast, but it is nice to have a try from for this. And finally, we're going to look at this set of 4. These are all for effectively arrays with constant sizes and converting those either into vecs, arcs, or RCs. This one feels a little weird to me, honestly. So if I comment most of this out and we look at the vec, we're taking an array, which is a 10 sized array of cars. In this case, they're all A's. We're going to print that out, and then we'll create a vec from a shared reference to that sized array, which is important. And that gives us a vec of cars, which we also print out. So in 174, this totally runs. And in 173, we didn't have the implementation to actually do this. So this was not possible in 173, and now it is, which is great. You can now create vecs from shared references to sized arrays, whether that is a shared reference or an exclusive reference. If we look at the types here, it is shared reference here and exclusive reference for this other one. Note that these also require the types to be cloned, which is an important note. So moving from vecs into arcs, right? In 174, this line on line 12 is ambiguous now. In 173, this code just runs fine. And the issue here is that we have a new additional implementation. So before we had arc for all T, right? If there's a T, you can wrap it in an arc, right? Now we have an implementation of from for Tn, where T is the type of our array and N is the constant numbered size. So in this case, it's, our array up here. This means that this array, when we do arc from, could use either of these implementations to actually do it. So what ends up happening in 1.74 is we do need to be explicit about these types. And we can be, and this will just run, which is great. Same thing happens for RC. RC cannot infer type because this line is now ambiguous because there's no type to pull from. Or rather, there are multiple competing implementations that could be used. And in fact, in 173, this code did just run. It works. So in 174, we just have to be a little bit more explicit about what we actually want to happen here. And that's because of these new implementations for generic T, const N, which is a U size. And we've got these arrays, which are of that type T and of that size N, for arc with an array of T and arc an array of T. Again, the constification of the standard library also continues. So we've got stir is ASCII or U8 is ASCII, as well as transmute copy. And finally, as was true in previous announcements, the minimum requirements to run Rust on Apple platforms, or not to run Rust programs, but to run the Rust compiler, is now 10.12 Sierra, iOS 10, and tvOS 10. That's it for 1.74 today. I hope you enjoyed it. If you have any questions, leave them in the comments. The links to all the code are in the description, and I will see you in the next one. Have a great rest of your day.